Okay, welcome back for the third half day of Curiosity on Mars session. So this afternoon we'll have the last part of the oral session and then a poster session in the red area. So it's our pleasure to start with Don Hassler, that will give a talk about the radiation environment on the Martian surface and during the cruise to Mars by MSL. So Don, it's all yours.
Thank you, Patrice. Yeah, so I'm going to talk about the results from the RAD instrument on MSL, which is it's a small instrument, but it's an international team composed of scientists from the US and Germany, Christian Albrechts University in Kiel, Germany, and DLR in Cologne, as well as Southwest Research Institute and Johnson Space Center in the US. We have several folks from the team here in the audience, and they have posters and talks later on today, and I'll reference those at the end. So if we visit for a moment the top-level objectives of MSL, of the Mars Science Laboratory, to assess the present and past habitability of Mars, most of the discussions to date have been about the geology and looking for carbon-based materials. But certainly, one of the elements that has to do with habitability is life-limiting, or factors which limit habitability, or life-limiting factors. And clearly, the radiation environment is one of those. And it also has relevance towards human exploration, because if we're going to send humans to Mars in the near or mid-term future, we need to know what the environment is and what to expect. So RAD is very relevant to the MSL mission, to its primary objectives, as well as to the human exploration objective as well. So why do we need to measure this? Well, there's two reasons why the radiation environment on Mars is different than it is on Earth or near Earth. Mars doesn't really have a global magnetic field like the Earth does to protect it from solar energetic particles and cosmic rays. And it also has a much thinner atmosphere. It's about 1% the thickness of the Earth's atmosphere. Just to summarize, there's two primary types of particle radiation in space and on the surface of Mars. One is galactic cosmic rays, which comes from supernova remnants far off in the galaxy, and they're very high energy, but relatively steady in terms of their fluence. They vary over the course of the solar cycle. And then there's solar energetic particles, which come from the sun. They're episodic, or they're difficult to predict. They can start on the order of minutes to hours and last for hours to days. And their energies vary widely, but they're very difficult to predict. And they also vary with the solar cycle, but they're highly variable. So just a quick overview of the RAD instrument. It's about the size of a coffee can or a bread box. It's about 1.5 kilos, and when it's operating, it operates with about 4 watts. And it's a combination of both a charged particle analyzer and a neutral particle analyzer, because we really want to characterize all types of spectra. There's secondary neutrons on the surface of Mars, and there's secondary neutrons inside the spacecraft on the cruise to Mars. So we want to measure the neutral particle radiation. That's also biologically effective for humans. But the primary radiation coming from cosmic rays are charged particles, ranging from protons and alpha particles or helium ions all the way up to iron. So we really wanted to combine two types of particle detectors, charged particle and neutral, all in one, with a common set of electronics to operate them both. And that was a challenge, because typically these types of detectors would be 10 kilograms. So I think one of the advancements and challenges of this was to package RAD into this 1.5 kilogram small box. This is a cross-section view of the instrument, but basically we have 3 solid-state detectors, very creatively labeled A, B, and C, as well as 2 scintillators, D and E. D is a cesium iodide, and E is a plastic scintillator. And so A, B, and C sort of define the telescope for the charged particle channel of RAD. So charged particles come through, and we have a coincidence system which detects a particle incident on any 2 of those detectors to be counted. And then we measure the energy deposit going through collectively each of those different detectors. The neutron channel, we have 2 different types of scintillators, and they're more sensitive to neutrons in the case of the plastic, or more sensitive to gamma rays in the case of the cesium iodide. So about a year before launch, we realized that we could operate RAD during cruise, sort of primarily the initial thought was as a calibration to compare with other observations from other spacecraft. But as we thought more about it, we realized it was an interesting and important observation in itself. Basically, RAD sitting inside the MSL spacecraft is not so different than what an astronaut would be like sitting inside the CEV or a future, a human spacecraft in deep space. And so we managed to take 7 months of data during cruise, basically to characterize what this environment would be for humans. I'm wondering if I got this out of order. Nope. Okay. So this is kind of a view of the shielding, the field of view of the Charged Particle Telescope through the spacecraft, and then here's all the elements inside. So we're not looking at the cosmic rays purely. We're looking through all this shielding, which has an average of about 28 grams on average, but it's highly variable, which I'll talk about in a second. And during cruise, we basically have this relatively stable galactic cosmic ray background, very high energy, mostly penetrating particles, but then these 5 episodic data from 5 episodic solar particle events, which were actually quite large. 2 of them were X-class flares, and the other 3 were M-class flares, which was fortunate for us because we were able to characterize what the radiation through this shielding would be for these different types of radiation. This is an example. This is just qualitative, not to be used quantitatively. To do that will take much more modeling, but this shows the RAD data in black, with the red data being from the CIS instrument on ACE with 30 MeV or greater protons. And it's really just, since both ACE and MSL were magnetically connected, this sort of shows the effect of the shielding in terms of reducing the radiation flux by about 2 orders of magnitude. If you look at the total, the total dose or dose equivalent, which is the biologically effective dose from all of these solar particle events, we get a number that's about 24.7 or roughly 25 millisieverts. The total from the galactic cosmic rays was on the order of 465 or 460. So if you sum them up, we get about 490 millisieverts, or almost 500 millisieverts of dose during this cruise. Keep that number in mind. I'll talk about it more later. But the thing to note is also that the total from these solar energetic particle events is just happened to be due to those 5 events. It could be very different if you have other events or larger events or smaller events. Some events in the past have been quite large. One of the things we're finding, and one of the important values of RAD, is to compare our data then with models. There's many GCR models out there, and there's many transport models out there, and so one of the primary objectives from the human exploration side is to compare the RAD data with these transport models. And so this is not comparing RAD quite yet, but this is showing just an example. Here in the purple triangles is the ACE-CRIS data compared with models from Bedware O'Neill 2010, various other cream models over the course of time over the solar cycle, and they agree to some degree, but not great, and all the models differ somewhat between them. And then solar minimum, there's actually a real issue. We had a long extended deep solar minimum, and they didn't agree quite so well. So using the data from MSL, from RAD, we can help to coordinate and compare these different models and to try to understand how to improve them. Here's the modeling that we did. Here's the results we have from the radiation dose inside MSL and the dose equivalent inside MSL compared to different models from the Ulteris website, which is a NASA operated website to model the radiation environment. These are using 2 modulation factors, 438 and 635, which is really just an estimate of effectively of the sunspot number or the heliospheric density or just the total volume of the heliosphere, which modulates the galactic cosmic rays. And then this is the amount of shielding through the spacecraft. And so if I said our average was 28 grams or 25 grams per centimeter squared, that fits somewhere in between here. None of these models agree perfectly, and they start to diverge more when you talk about dose equivalence. So I think coordinating the comparison within the models of the different groups, I think, is an important goal over the next year with RAD. So we turned RAD on the day after landing. I think after the cameras, we were the first instrument that we turned on. So on August 7th, which serendipitously turned out to be the 100-year anniversary of Victor Hess's discovery of cosmic rays from his balloon in eastern Germany, we actually are measuring the cosmic ray spectrum on the surface of another planet. And I thought that was really cool. And a fitting statement about the progress we've made in the last 100 years. Here's a photo of RAD on Mars from the cameras. Here's our protective window. You can see some of the debris from landing, and then the backdrop. That's just a pretty photo. These are the data from about the first 100 days, 100 sols on Mars. You can see variation, which occurs. The large-scale variation is on the order of tens of days. The sun rotates with a 27-day cycle, so you can see a modulation, which is from the heliosphere, which is driven by the sun on roughly a 27-day cycle. You can also see a daily variation or a diurnal variation due to the atmospheric pressure. It turns out, and as was discussed this morning, the REMS pressure varies by roughly 10% over the course of a day. The REMS data would be in blue here. And then we find that the charged particle dose on RAD varies inversely to this, that the charged particle data, as the atmosphere is thicker, there's more shielding, and so the charged particle dose from RAD goes down. Ironically or curiously, the neutron flux, which is a result of nuclear reactions or interactions in the atmosphere, actually is positively correlated with the observations with the atmospheric pressure. And so we actually see, you can sort of see here, as the charged particle flux is up, the neutron particle flux is down. And this is being worked on and discussed in a poster that's being shown this evening. So summarizing this, after the first, say, roughly 100 days on Mars, what does this mean for a human mission to Mars for the future, for example? Well, these are the measurements before, where I talked about the total dose rate. I guess I got to get my consistency here between this plot and the previous one. There was an update, but roughly between 450 and 500. Oh, that's in gray. I'm sorry. That's a different unit. But the total cruise dose equivalent rate was about 1.8 millisieverts per day. That's just a number. And on the Mars surface, about 0.7 millisieverts per day. If you compare that to things that we know, a chest X-ray is about 10 times less than a day of radiation on the surface of Mars, and the natural background radiation is about 50 times less here on Earth. But if you're on space station, it's on that order, maybe a little bit more, maybe a factor of 50% more on the surface. But in cruise is where the big difference is. Cruise is a big number. If you talk about that for planning for a future human mission, it's a little bit more difficult because no one uses a hard limit. A lot of agencies talk about 1 sievert as a rough limit, but that number depends on age, it depends on gender, it depends on health history of the astronaut. In the case of NASA, it's based on 3% excess career fatal cancer risk. And for, say, a 30-year-old male, that effective limit might be 0.6 sievert, whereas if you're a 55-year-old male, it might be 1.5 sievert. These are just numbers, but if you compare these numbers with the numbers we're getting, it gives you an idea of the challenge we're facing for sending humans to Mars. So if we look at, say, a design reference mission, which is one of the things that folks are talking about, even the private and even in the private sector now, if you look at these astronaut career limits, so say, half a sievert to a sievert on that order, you look at the total dose equivalent that one would receive on the way to Mars on the order of, say, 350 millisieverts for a 6-month mission. And then say, well, you have to decide how long you're going to stay on Mars. So obviously, the longer you stay, the larger dose you get, but it's a smaller factor than during cruise. So if you have a total mission dose equivalent for a 300-day mission, that might be on the order of 0.9 sieverts and about 1.1 sieverts for a 600-day mission. So once you get there, the dose rate goes down compared to being in deep space, but you got to get there and then you got to get back. What's exciting for lots of reasons, we're right in the middle of solar maximum. We saw those solar particle events during cruise. As we start to decline in the solar cycle, we expect to see more solar particle events. We have yet to see one from the surface of Mars, so we're looking forward to that opportunity. And then as we get towards solar minimum, the galactic cosmic ray background will probably go up significantly, perhaps as much as a factor of 2. So it's an exciting time for making these measurements. And we have, let's see, 2 posters, which you can see this evening between 5:30 and 7. Kerry Zeitlin presents more quantitative results from RAD, and Scott Raffigan is going to talk more about the diurnal variation that we're observing from RAD. And then there's a related talk which Bob was scheduled to give at 4 o'clock in another session here in this room, and I'll be talking more. I'll be giving that because he couldn't come, and it talks more about the onset times. So thank you very much.
Thank you very much. We have time just for one question. Okay. You can go to the microphone.
Can you tell us, do you split into channels, energy channels, the neutron fluxes on the Mars surface, or is it just an integral count?
No. This is just a very brief overview. That is the strength of RAD, that we actually measure energetic particle spectra for all particle types. So we're just producing those first spectra for protons and helium. And I'm not sure if that's being presented in the poster this evening, but we're just starting to do that, even spectra for iron, as well as the inversion for the neutron data and the gamma ray data. But it's early in the mission, and we're heavily involved in ops as well, so it takes time to get all that together.
Okay, thank you.
Yeah.
Thank you very much.
Yeah, thanks, Patrice.
So next talk is by Igor Mitrofanov on testing water in the soil of Gale by Dan.
Yes, it is my pleasure to present you the first results from DAN instrument on board rover Curiosity. And I'm speaking on behalf of the large team of people which are working together in the research centers both in Russia and in the United States. And in these centers, people are working both for space science and for nuclear science. And DAN is very much associated with the nuclear science, so I will continue the field which was initiated by Don in his previous talk, and I have to speak a little bit about the physics of our measurements. In not only cosmic rays, but artificial neutrons which are producing by our generator are propagating to the subsurface. And in difference from the natural cosmic rays, in this case, the flux of neutrons has very short time, about 2 microseconds. These neutrons penetrate to the depth about 60 centimeters during these 2 microseconds, but it takes a lot of time for neutrons to leak out, to escape from the subsurface, because they have many collisions with the heavy nuclei. In each collision, the particle loses a little bit of energy, and this axis corresponds how the energy is decreasing in this diffusion process. And also, the particle takes a time to go outside, and this axis practically, in sense of physics, like a parallel line with decrease of energy. It is a time delay of particle. And finally, when particles are already several orders of magnitude less energy than the original one, we have them epithermal or thermal particles, and we see this die-away curve, this time-delayed profile of particles which escape from the subsurface. And this illustration corresponds to the usual situation when we have basically only heavy particles. In case of presence of hydrogen, I just want to remind you that hydrogen has a proton as a nuclei, and proton and neutron are the same nucleons. And in the case of collision with a proton, a neutron loses a lot of energy, go more rapidly to the thermalization end of this curve, and spend longer time because of smaller velocity in the subsurface. So effect of the presence of hydrogen is both increase of the flux of this emission of neutrons, delayed emission of neutrons, and also longer time of this emission. And this is an important property of this method of active neutron sending. In case of galactic cosmic rays, there is no time-dependent resolved measurements of neutrons. So in this case, the presence of hydrogen will only be responsible for smaller flux, less hydrogen, or larger flux, more hydrogen continuously, constantly. So we are able both to measure in this passive mode when we use just our detector unit, which measures separately epithermal neutrons and thermal neutrons. And this part of our instrument has a heritage of hand instrument, which is now working in space more than 12 years on board Mars Odyssey. And as I explained to you, important part of instrument is a neutron generator, which produces the pulses of these 14 MeV neutrons. This generator has no flight prototype. It is the first time when neutron generator is operating in space. The prototype for this instrument is based on the industrial pulsing neutron generator, which was developed in Rosatom Corporation for the geological screening of the subsurface for oil wells. And the part of the generator we just produce neutrons is this vacuum tube, which just a place where the thermonuclear reaction takes place when deuterium and tritium produce alpha particle and neutron. Using this, excuse me, just to tell you that we also participate in the program of dosimetry, as Don introduced. And please listen, Dmitry Golovin talk this afternoon about our contribution to the measurement of radiation dose. Don is measuring high energy neutrons from cosmic rays. We are able to measure thermal and epithermal neutrons, and we are able to measure them as a product of bombardment by galactic cosmic rays. And today I will focus on the data of the surface measurements along the Curiosity traverse. A lot of people already shown this traverse in the previous talks. And the result of our measurement, the empirical data, is presented here. Along the traverse, along the meters of the rover path, we present here the measurements in active configuration when we radiate neutrons and when we measure time-dependent signal from the subsurface, and we are able to resolve not only the content of water but also structure of water deposition. And in parallel, we do these so-called passive measurements when neutrons are produced by galactic cosmic rays and RTG on board MSL. First of all, there is all effect excluded here from our data. We take into account variations of cosmic rays. We take into account variations of neutron generator profile. So this is just the only subsurface dependent curve, and we see that it is quite a good comparison between these two curves. For people of future ExoMars rover, I would just want to tell you that in the ExoMars we plan to put similar neutron instrument but without generator, so the profile which will be detected by ExoMars in some another landing site will be similar to this reddish curve. So now I will go to the main result. Before I go to estimation of water, I just want to tell you that Ruslan Kuzmin present today, this evening, the poster which will discuss more the correspondence between our neutron data and the morphology on the surface of the planet. And also, Alexey Varenikov will speak on Friday about exact process of data deconvolution, how we go from the experimental data for neutrons to the which is associated with the presence of water. This process is model dependent, and we do different testing models. We compare them with experimental data. And finally, we get the curve which produced to us all estimations of water from different models. And the most probable values are presented here by the cross. First of all, we see a very good physical relationship between the flux of neutrons and the content of water. And actually, passive mode is able to measure such a total water measurements, but the passive mode is not able to study the subsurface structure of water deposition. And the second main result is that variations of water along the Curiosity traverse is somewhere between 1% of weight up to something like 2.9% of weight. In different spots, we have different results of water subsurface. In many cases, this is just a homogeneous in-depth presence of water with a standard density and chlorine about 1 weight%. In some other cases, we see the two layers model when dry layer has about 2 times less water than the layer in the subsurface. And the thickness of this layer, we believe, may be associated with the thermal blanket thickness on the surface of the soil. It is interesting case when we see the inverse situation when the top layer have more water than the layer in the subsurface. And we have to study these cases more to understand the physics of such deposition. And in the minimal case of water, the Rocknest, we just see the presence of water, which is about 1%. And similar we see in the Point Lake area and in the Gillespie area. And finally, in the Yellowknife Bay, we see in many points, again, this standard model with a dry layer on top, the water-rich layer. The fraction, the difference is about between 2 and 3 times between them, and the depth of this water-rich layer is between 5 to 20 centimeters. And this is my final conclusion, which I would like to emphasize not only our results, but also problems which we see in the analysis of our data. So the first, we have these estimations of water along the 700 meters of the traverse of Curiosity, between 1 and 3%, together with the average chlorine, about 1%. And these values are average values for the depths about 60 centimeters, the depths of penetrations of our neutrons. The problem is that orbital data from Mars Odyssey shows, this is a part of map from Mars Odyssey which present the weight percent of water. And this bluish region here corresponds to about 5% of water average in the same depths of subsurface. And also Mars Odyssey give us a smaller value of chlorine from the orbit. So we have to, we all remember that spatial resolution of instruments from orbiter is about 300 kilometers, maybe 500 kilometers. So these values should be corresponding to very large area around the Gale, but the ground truth in the Gale happens to be different from our expectation from the orbit. We have to understand that, we have to get more data, and probably if it is the average value, there should be somewhere areas with much more water than the average value from the orbit. Second point that I already mentioned, that we have not only homogeneously distributed water, but also water in the layers. And in the majority of cases, we have something natural when the dry layer is on the top of the wet layer. However, there are 4 confident tested spots when we see that more water is on the very top subsurface. This layering structure, again, agrees very well with the data from Mars Odyssey, which show both in neutrons and in gamma rays that we have less water in the first several centimeters or tenths of centimeters. And this case is something new. We have to make more data, we have to make more physics to explain this phenomenon. Thank you very much.
One question, please. No questions? Thank you very much. So next talk is by Susanne Schroeder. She's going to talk about first analysis of hydrogen in ChemCam spectra.
Okay, so hello everybody. I'm going to talk about the analysis of hydrogen in the ChemCam spectra at the Curiosity landing site. I did that together with my team in France and in the US. And what you can see here is the first target or the first victim of ChemCam on Mars, which is a rock called Coronation. And we shot with the ChemCam laser on it on Sol 13. Below you can see the LIP spectrum, laser-induced breakdown spectroscopy. So you can see the 3 wavelength ranges we see with ChemCam, which is the UV, the visible, and the visible to near-infrared region. And I marked here all the elements we can see with high intensity in those spectra. So this is mostly the major elements. Which are marked here, and also we can see some minor and trace elements here, including the carbon and the hydrogen. Enlarged here is the hydrogen and the carbon peak, so they are overlapping. The carbon is in all of the spectra due to the carbon-dominated atmosphere on Mars. So the hydrogen is here on the edge, here. And the next slide shows another example of the hydrogen in the Rocknest soil. So these are 4 mean spectra of the Rocknest soil. You can see that the hydrogen is varying a lot, and the calcium and the carbon are more or less constant. So this is a pretty nice spectrum, and it's the process data. So the dark spectra are subtracted, the background and the noise are removed with an algorithm, and also they are wavelength calibrated. And this hydrogen results, or this hydrogen line results from a transition from the second to the third, from the second to the first level in the hydrogen atom. It's the most intense hydrogen line, and it's also usually the only one which is detectable with ChemCam. Generally said, the spectral line intensities are influenced by many factors. So, for instance, the abundances, the transition probabilities, and also the spectral response, which is a function of the wavelength. So this is how, this is a little bit about data processing, which is very important for the hydrogen line because of 2 reasons. So first, we are measuring something which is called dark spectrum, which is integrated for the same time than the active LIP spectrum, but without the laser. And we do this to account for the reflected sunlight, the pattern noise, and the counts due to the thermal dark current. You can see it in orange here in the plot. Also, you can see the raw data plotted here in blue. So when we subtract this dark spectrum from the data, you can see that there's still remaining offset, which we call background. And this is due to the continuum radiation, which results from Bremsstrahlung and recombination of the plasma. In comparison to this background, the hydrogen line is not very intense. You can see this here. Also, what you can see from this plot is the high hydrogen in the first shot spectrum. This is due to the dust. And as I said, this can be seen in all of the data. So the dark spectra are very important for the hydrogen line because of this hydrogen Fraunhofer absorption line due to the solar spectrum. And we wondered whether it's better to get the dark spectrum before or after the LIBS analysis. So what we did is a special sequence on a fine-grained soil. We did one laser shot, one dark, one laser, one dark, 10 times. And you can see the results plotted here from blue to green, 10 times. And the most contribution of this dark spectra, you can see this is indeed in the region where we have the hydrogen line. And from our analysis, we found, here on the right, you can see first that the darks are getting darker because of the laser drilling into the soil, so the reflected light gets less and less. And for most of the data, we found that it's better to get the dark spectrum measured after the active LIBS measurement. And we checked if this is also okay for the hydrogen line and did the ratio before and after, which is constant, so there's no problem for the hydrogen line. For quantitative analysis with LIBS, there are mainly two approaches, which is the univariate analysis and the multivariate analysis. For the univariate analysis, we have the assumption that the line intensity of the emission lines is a function of the elemental abundance in the sample, which is at best case linear. But the problem with LIBS is that there are chemical matrix effects. So the emission line intensities for LIBS cannot always be related to the abundances. And this is in particular true for the hydrogen. So this might show up as adsorbed water at hydrated minerals or also chemically bound. So what we are doing with ChemChem is multivariate analysis, which is a statistical approach and takes into account several variables at one time. So we are doing partial least squares analysis, which is short PLS. And with ChemChem, we can predict the abundances of all the major elements, but not the hydrogen. And both data sets, or both approaches rely on a laboratory database. So we obtained the spectra obtained under simulated Martian atmospheric conditions, which is the pressure and the composition. And this database has to be extended, in particular, to make quantitative analysis for the hydrogen. So that's what we have to do. And what I'm going to show here is univariate analysis, so it's just trends. And I have to remind you that the data which I show you, you shouldn't use them to compare different matrices such as soil or rocks. So what I'm doing, as I said, the hydrogen line is superimposed by the carbon line, and I'm fitting both lines simultaneously. And here are some definitions. So the signal is the amplitude, here in red. You can also use the peak area. It's more or less the same. Noise is a standard deviation in a peak-free range close to the hydrogen line. Background is a mean in the peak-free range close to the hydrogen. I remind you, this is due to the continuum emission. And so what I'm giving here is the signal-to-background ratio, short SBR, which is the signal divided by the background. And you can see here coronation, the rock, as an example. The background and noise are more or less constant, with only little variation. And on the right, you can see the signal-to-background ratios. For the hydrogen, this is a trend which is very typical for all the rocks we see on Mars. So the high hydrogen signal in the first charts due to the dust, and then the carbon, which is more or less constant, which is the contribution of the CO2 of the atmosphere and the breakdown of the plasma. After the dust is removed, the values of the hydrogen signal to background are pretty low, but it's not nothing. So there's still some hydrogen in the rock. And to say what is really nothing in terms of signal to background on Mars, we investigated the onboard ChemChem calibration targets. So we have 10 targets on Mars, 4 ceramic targets, 4 synthetic glasses, titanium and graphite. And on the right, you can see that after the dust is removed, a mean value of about 0.08 is obtained, which we say this is no hydrogen. So this is used as a blank value. On the left, you can see a picture of an RMI on Rocknest rock. And you can see that with ChemChem, we are removing the dust from the sample. So the spot size is 0.5 millimeter, and the band which you can see here is 1 centimeter. So the ChemChem plasma shock wave removes the dust. And how do we know the hydrogen which we see in the data is really coming from this dust? So we had a look at another calibration target, the graphite. And also the first shot composition is clearly not what is graphite, but made of other elements in the dust of the Martian. So this is about hydrogen in dust, soils, and rocks. So we took all the data we had and plotted it, the total intensity of the third wavelength range versus the hydrogen line. And if you mark the first shots, you can clearly see the dust in those spectra. And again, this is hydrogen over total intensity, so this is a constant, which means that the hydrogen signal from the dust is constant. When you now select all the soils, which we did with the RMIs, so visually, and mark them in green, you can see that for the soils there's lots of variation. And here, more hydrated, that's more or less the fine-grained soil, whereas the coarse-grained soil plot more here. And if you mark all the rocks we targeted so far with ChemChem, you can see that they all show up with the low hydrogen signal, but it's, whoops. But it's not nothing. So also for the rocks, you can see that there's still the hydrogen signal in it. And some of the rocks show even higher. Higher hydrogen signal.
Sorry, keep talking.
Okay, so next slide. This is about the hydrogen in soil. And again, here can be seen that there's lots of variation in the ChemChem data for the soils. So, whoops, sorry. You can see here there's lots of variation in the background, also can be seen here. And also there's lots of variation in the signal intensity of the hydrogen. And generally, it can be said that the soils, they have the higher hydrogen signal in comparison to the rocks. Okay. We did another investigation on the crystalline soil. Actually, this happened before the other one which I showed. So you can see here the undisturbed soil, the first shot and the second shot. And the aim of this study was, is there an exchange of the water or frost deposit in the upper millimeter during night? So we did a measurement during Martian day and also one during Martian night. You can see the times here. And what we found is that there's actually no enhancement in the hydrogen signal overnight. So you can see here the hydrogen signal for night and day plotted in black and gray, and also the signal for the carbon line. And there's no variation, so at least we didn't find it. And this is probably due to less than 1 weight percent, which is a calculation, more or less quantitative, based on the SAM value of the water at Rocknest as an in situ calibration point. So to sum up, conclusion and outlook, we see the hydrogen everywhere. The qualitative analysis of hydrogen is relatively straightforward, but the quantitative analysis is more challenging due to the matrix effects we have with ChemChem, but it is in progress. So we will expand the laboratory database and with special regard to the hydrogen, and we'll use multivariate analysis methods to get to the quantitative analysis for the hydrogen. From the signal to background ratios, you can see the typical trends for rocks, which is the dust and then little variation, and also the soils, which is the higher hydrogen signal and more variation. And by this, you can also identify coarse grains in the spectra. And we found the hydrogen dust on all of the targets on Mars in every position and on every target we shot. And so for the soils, we didn't see variation of the hydrogen signal during night, and also not with time and depth, but this will be presented in the next talk. Thank you.
Thank you very much. Any questions?
Were you able also to measure the Balmer H beta line at 4860 nanometer in order to disentangle abundance from excitation, or also partial lines, for instance?
We are not very sensitive at that wavelength range. So usually when there's high hydrogen, we see it for the hydrogen alpha line. The hydrogen beta line with this setup, with this experiment is almost not visible. We checked that. It's too low.
Okay.
Okay, thank you, Susan. Okay, we will move to the next talk. My pleasure to welcome another researcher from ChemCam, Olivier Forny, that will talk about diversity on soil viewed by ChemCam on behalf of Pierre-Yves Mélin. Olivier, it's all yours.
Thank you very much. So, Pierre-Yves Mélin, who was supposed to do the talk, could not attend, so he apologizes. And I will present the results on soil diversity along the traverse, which is the result of the input of many people and not only from ChemCam. So here we have the first soil we get on the traverse, which was on soil 19, which is beachy. You see the the traces of the 5 spots. And generally in soils, the spots are large because the material is loose. What can we learn from ChemCam for the soil analysis? So we have the possibility to isolate different soil components and bulk ones. We can have the possibility to have a 3D chemical profiles, which with X and Y with the location, diverse location, and also depths. Typically in soils, we reach few millimeters depths. We are sensitive to the major elements, as Susan said, and also to trace elements like manganese, strontium, chromium, barium, lithium, and rubidium. And of course, as you saw earlier, sensitivity to hydrogen. We have a large statistics on soils. We have, during the first 100 soils, we have 19 soils targets and 136 soil points, which represents more or less 3,600 spectra. Here on the traverse route you saw already. Here are the soil we get during the traverse. Here are the soils in the Hummocky region, and here we got a lot of soils on the Rocknest region. So what are the soil diversity we can encounter? So we got this soil diversity by means of different techniques. One are qualitative, like classification or relative, like independent component relative intensity and cluster analysis. And we have also quantitative measurements with the PLS that Susan described here, a few minutes ago. So we here on this plot, you have in black, you have all the single shots we got on soils, and the colored points are the mean of all these points. So the first group we identify is a felsic type class, which has more or less 60, which is enhanced in silicon, alkaline, and aluminum and alkaline, which has more or less 65% silicon contents. And then we have a branch here where the soils have enhancement in magnesium correlated with chromium and manganese, hydrogen, and you see that they are depleted in iron and titanium. And in this branch, we have two groups that separate. One is enhanced in hydrogen, the other one is sodium and potassium and aluminum. This is an intermediate group. And the final group, which is the mafic type group, which has low silicon and it's enriched, as I said, in hydrogen and magnesium. So what about grain size? Since the The laser spot is around 0.5 millimeter. What we call coarse grains are when we hit a source, are grains that are larger than the leaf spot, and fine grains are, on the contrary, here on cluster home, are spots that are much larger than the grain size. So on the same plot where we have all the shots, we see in the light gray tone all the coarse grain shots, and on the black points are the fine grains. How do we disentangle between the two? When looking at the spectra, we say we have a coarse grain when either the composition, either the intensity is more or less constant. When it varies a lot, we say we have a fine grain. And you will see, you see that on these slides that the first type, which is mostly dominated by coarse grains, are located in this high silica region, with which we have Stark, as that was presented by Viren this morning, Link, which is a conglomerate with large grains, and Mara. And we think that the soils in these regions are from local origin. Then they are similar in constitution to the rocks I've told about, and we think they are transported and deposited as part of the Peace Valley alluvial fan. And the fine grain end member, we think it's the global dust we see on Mars. And with the same composition, we see the main average soil, which has been defined on Mare by McLennan and co-workers. Here is the APXS portage point on the soil, which fits at the center of this ellipse. And we see that the dust is also close to that. So we think that the fine grain soils are a global component, which can also be encountered in the Rocknest baked form. So to compare rocks and soil in the Rocknest area, as I told you, we see a clear difference between soils and rocks by the argument that the rocks are more iron and titanium rich against soils that are much iron and hydrogen and magnesium rich, and this is clearly can be shown here, where we plot here is the iron and titanium. The scale is a relative scale; it doesn't represent the composition, versus this magnesium and chromium and manganese component, and you clearly see that Rocknest soils are enriched in that component, with contrary to the Rocknest soils, which are enriched in iron and titanium. So, do we detect some salts in rocks, in soils? When we do this plot on the soil, this is the silicon content versus the missing component of our quantitative analysis, because we cannot identify sums quantitatively identify these elements. LIPS is bad for this sulfur, chlorine, phosphorus, and fluor. And we see this kind of anti-correlation between silicon content and missing component, which is also can be seen here with this anti-correlation between silicon and calcium. So this means that the soils are more hydrated, but the missing component is correlated with an increasing of calcium, and this calcium is probably associated with the missing ions we don't see and not measured by ChemCam. So we have some hints that we have detected in this kind of soils, chlorine or phosphorus. So maybe this missing component is associated to calcium sulfate or calcium sulfate or even perchlorate. And on some points on some rocks, we see Pearson rocks who have 2 points here, which are also depleted in silicon and enriched in calcium, in which we see this line. So these soils here may be originated from that this high missing component can be associated to these rocks. So as Susan said, we have the soils show a very high hydrogen line, as I showed already. The hydrogen peak is high. So, and this is almost the fine-grained material which is enhanced in hydrogen, and it controls all the hydrogen set. You can see here on this hydrogen intensity versus the sodium intensity that all the mafic type rock fine grains are enhanced in the hydrogen, and the rocks aren't. So, and we see that the dust falls into the same type. So the fact is that Chemin didn't detect any hydrated crystalline minerals. So we infer from that the hydrogen is carried by the amorphous phase detected by Chemin, and also by adsorbed water. So the question are now, does this hydration varies with time and with depth? And Susan has already answered to that question. In depth, we have on this trench, we had data on the surface and into the trench at various on various spots, and we don't see any variations. And when we do some histograms on the population of spectra from the undisturbed surface and soil and on the area of the trench, we don't see any significant difference in the hydrogen content. So this is for depth, and as already showed by Suzanne, we had a day-night observation, and also on the same trench, the data were acquired at 11 sols from differences, and we don't see any variation in time. So to summarize, we have analyzed the soils during the 91st soils, and we think the soils fall on a mixing line between a local coarse-grained felsic component and a fine-grained mafic component, which are similar to the average Martian soil. And Chemin didn't detect any hydrated phase in the Rocknest soil, so the water seems to be carried by the amorphous phase. The mafic component was incorporated in all the soils and analyzed by ChemCam, and it controls its level of hydration by mechanical mixing. And the observed hydration could account for a significant fraction of the global Joule share of hydrogen that has been observed by Omega, for example, in the 3 micron band absorption depth, or by the GRS neutron detector. And ChemCam does not see evidence for temporal or spatial variation of the hydrogen, and this means that we have a limited specific surface area of the soil inferior to 20 cubic square meter per gram, and this can put constraint on the natural amorphous state phase detected by Chemin, which tends to see halophanes, but halophanes that have a much more specific surface-specific area. So this is we have a large data set that will be we will have more data during the oncoming observation, which can give us constraints on global, regional, and local sources. And I'll stop there. Thank you.
Thank you, Olivier. We have time for a very quick question. Okay, then we'll move on to keep on the track. Thank you, Olivier, again. So we'll now welcome Walter Goetz, that we talk about compositional variation of a place on Mars called Rocknest in Gale Crater, surprisingly. Walter, all yours.
Okay. Thank you, Chairman. On behalf of my co-authors, here please read through the list. I'm going to talk about compositional variations of Rocknest sand. So I will not talk about the entire traverse, as was done before by talks by Olivier and Suzanne, but I'm talking only about a tiny spot. This is Rocknest deposit, but still we have spent there about 40 sols, so something must have come out of it. Here, very briefly, we come from this western direction. You can see here, you can see the wheel tracks arriving here at Rocknest deposit with the dimensions as specified, and then we were looking here at the pristine surface, here the yellow rectangle, and zooming up we see a wonderful image, and this is the top surface of Rocknest deposit, and you can see nice sub-rounded millimeter-sized grains. Here is a scale bar on the lower left, but even more interesting, you can see, if I go back and forth, you can see some cracks in this top surface. And you may say, oh, they are just, they outline the shape of the sub-rounded particles. Actually not. Many of these cracks here are rectilinear, so they deviate from the shape of the sand particles. So, and some cracks here have a very irregular shape as this one. So you can see also very nice here, up here, you can see cementation. So I'm in the center of my talk talking about chemical sediment cementation. And this also tells us that this deposit has been immobile for quite a time, so that cementation can develop. Okay, and then you see, wow, between Sol 60 and Sol 65, we made a hole. It's right there. Zooming in on this rectangle here shows us this image. This is a Marley image, and you can see the coarse-grained particles on top, and then a grain size gradient downwards, smaller particles here, and we have a gradient in color also, or in albedo, as you can see here. Note the bright band continuing here on the near side, and you can see angular fragments. And you can see these angular fragments, they fell down onto the floor and remained intact. So also this tells us there is cementation going on. And then here by Sol 93, we have made 5 holes, and zooming in on that, here is the image. And what you can see again is the bright band here, very well visible here. And then we really wanted to know, could it be a scooping artifact? Or is it indigenous to the Martian, to this deposit? And then we went out with a robotic arm and made an image with the Marley camera that is mounted to the end of the robotic arm, to the turret next to the Apex S. And here you can see overlying, you can see indeed the bright band continues on the near side. So we conclude that it's really an indigenous feature, and we have more arguments on that I'm not going to show here. So just for fun, here zooming in on this rectangle, here you can see this Marley image, and then zooming further in on this rectangle and this one, first this one. This is, well, a nice image here. You can see the narrow reentrant, again a sign indicating the crust, but also this is actually my favorite image, so I had to put it at some point in the talk. And here you can see almost the crust here, or a piece of the crust below this monolayer of coarse-grained sand. So it could be something else, but let's say I consider this as being a crust. And so something chemical is going on. And of course, we had to study, and we studied the chemical, the subsurface chemically with ChemCam. And zooming up on this part here shows you some holes here made by the ChemCam laser. And you can see there are several holes here. I will only talk about this lower left here. And there you can see different holes. We started on the bottom, one spot, and we shot 30 times at the same spot. Okay? Then moving up to the next spot and shooting again 30 times. And so on until we reach spot number 10. We made another run. You cannot see the laser holes here because the image here was acquired 4 sols before we made the laser experiment. But I will talk about these 2 runs. In particular, the red run here, which we call Canyon High Albedo. As you can imagine, we made the distance here is a little bit, the distance between different spots is a little bit smaller, is smaller than for Canyon, but we remained mainly within the bright band to see if we can see some chemical signature. So how do I present these two data sets? Well, I chose to choose here this diagram: aluminum to silica to silicon. The weight ratio is plotted on the y-axis, and the weight ratio iron plus magnesium divided by silicon is plotted on the x-axis. And in this diagram you have a couple of minerals that are there. Nontronite would be here, andesite would be up here. Sorry, that's outside of the coordinate systems, but doesn't matter. Here is albite, silica, augite, pigeonite, olivines, and so on. And this is the basaltic area. APXS, this is the average chemical composition as measured by the alpha particle X-ray spectrometer on board the rover. And it's here as published by Yen et al. In LPSC. And then we have here these multicolor color points. These are 30 dots here. These are the 30 shots. And you can see shot number 1 has a blue color. Shot number 10 has, for instance, a green color. Shot number 20 a red one, and shot number 30 would have has a yellow color. So you can see exactly when shooting these 30 shots what we see. And you can see we always we always start. The blue shots, the first shots, are always within the dust circle. The first thing we always see with ChemCam is dust, as Sylvestre Maurice, ChemCam co-PI, told us on Monday. And we start here, and then it evolves into some direction, okay? And you can see already the power of ChemCam. Each shot gives us a chemical composition. So by now we have got 44,000 chemical compositions by ChemCam. And let's see how it evolves. So here we have spot number 2. Watch out, the map here. Now we are at spot 2, exactly here. And we see 2 outliers. These are magnesium-rich pyroxene and or olivines. And then going on here, spot number 3, moving upwards, 4, and then 5, we are in the middle of the bright band. Well, this is the most mafic composition we have seen. And we don't know really what it means, but this is what ChemCam tells us. And then going on, here spot 6, spot 7. Look here, the data are scattered. Okay, they are scattered in this diagram. But now going from spot 7 to spot 8, totally different. And here you see, except the dust, we disregard it now. But we just all the points plot here, outside the basaltic area. So this means and also the scatter. If you compare to the previous one, a lot of particles scatter. The plasma shock wave moved around the particles, so we see a lot of variation in composition. Here, we hit a solid grain. So we made a depth profile into the solid grain. The plasma wave could not move around particles, okay? So therefore, all the particles are here at the same location. And then you can, we have, and our interpretation is that this should be a high silica, a silica-rich alteration phase on a solid particle, okay? So it could be a thick coating, for instance. But it is, what I also want to point out, if somebody heard Dave Wannemann's talk on Monday about chemin, it is not it has not the chemical signature of the amorphous phase we also find in the soil. So further on here, this is spot 9. Spot 10 again, we go outside the basaltic area as before, but interestingly, here we are moving a lot across this diagram. We start first shot around here, going over here, and then going over there and ending up here. You can see it by comparing to the color coding. So here we saw we hit a lot of different phases. And then for completeness, also showing the other, the narrow spaced run here, not so spectacular. We are moving up here. Interestingly, you can see again, we had fine-grained soil, but this, here we hit a mineral phase on a bigger mineral grain. And then here, for instance, we hit 2 mineral phases in a bigger grain. You can see, again, the data are concentrated in narrow areas on this plot. Okay, finally, I would like to address, I would like to show the same data once more, but plotted differently. And here showing the abundances, the major elements in weight % on the top right, and the abundance, the relative abundance, maximized, normalized to their at their respective maximum here for minor elements down here. And you can see, first of all, this was the famous particle 8, spot 8, I just described, the high silica alteration phase. So we need to distinguish, as I tried to explain, we need to distinguish between larger grains and the chemical signature of fine-grained material. Because the chemical signature of fine-grained material, it can tell us something about the post-depositional pedogenic history. Whereas the large, if we talk about the chemical signature of the bigger grains, they can tell us about the late pedogenic history, but they can even more, even more likely, they will tell us about older chemistry. Because if we look at the chemical signature of larger grains, well, this is the chemistry of grains that have been transported to the current location in the Aeolian regime. So interesting, if we want to study the Rocknest and what happened at this exact location, we need to look at the fine-grained signature. And we have, not all these points are large grains. We have also, for instance, spot 4, spot 7. These are fine-grained materials. So we have some chemical signature in the soil. And downwards. So here, by the way, I forgot to say, this is plotted versus the spot number, so versus depth. So spot number as being a proxy for the depth. And then here you can see the minor elements here. Hydrogen, here we need to, I need to discuss with Olivier. I see some variation here, but this is only for this particular run here, for Kenyon. And interestingly, the hydrogen is highest in the bottom of the trench. But then we have here also high lithium and high potassium at some places in the subsurface. Reaching the conclusions, ChemCam is an ideal tool to display chemical diversity on a near microscopic scale. ChemCam data scatter allows us to separate chemical signatures according to particle size. And that is very important, as I explained before, for the geologic interpretation. And then ChemCam found particles not seen by ChemIn. So this must be a particle that is below detection limit. And for ChemIn, and in this case, a silicon-rich alteration phase. And then we see some correlation, chemical correlation, some chemical variation in the subsurface, but poor correlation with the bright band. And finally, the ChemCam data are consistent with some vertical chemical transport that could be driven either by a changing environment. Think about high obliquity, a snow cover in the equatorial regions that could drive a vertical aqueous transport, or it could be driven by diurnal thermal cycling. Note that the chemical variations we have looked at refer to the uppermost 4 centimeters. This is exactly, or this coincides with the thermal skin depth. So we wonder if there could be a connection. Thank you.
Thank you, Walter. I'm sorry we have to move on, but I encourage everybody to speak to all speakers during the poster session, because we have a session very, very close by. So next talk will be given by Cyril Zopa, and he will especially talk about the detection of some volatiles by SAM gas chromatograph at Rocknest.
Thank you, Patrice. So you had a few talks about the analysis of the atmosphere with SAM, and I will focus on the analysis of the sample collected at Rocknest with GCMS, meaning gas chromatography, coupled with mass spectrometry. And here's a slide summarizing SAM for the diodes. And we see that the objectives of SAM are mainly to characterize the atmospheric composition, but also the composition of the soil samples collected by Curiosity, to determine information about the past environmental conditions in Gale crater, and also to assess the potential habitability of this site. So to summarize, SAM is a big instrument in Curiosity, composed of 3 independent instruments. TLS, which is an instrument focusing on the analysis of CO2, H2O, and CH4, and a gas chromatograph coupled with a mass spectrometer, which focuses on the atmospheric analysis and gases evolving from the solid samples. So the gas chromatograph goals are first to separate and identify the most abundant compounds present in the atmosphere and also in the solid samples, with a limit of detection of approximately 10 to the minus 10 mole. And it is coupled to the mass spectrometer to obtain a fingerprint of the compounds separated with a GC, and also to reach for a better limit of detection, because the QMS detector is most sensitive than the detector present in the GC. So the GC that you can see here, implemented in the flight model before the launch, is composed, in fact, with 6 modules, which are independent, each module focusing on a range of specific species. So most of these modules are devoted to analyze organic compounds, but you have specific modules separating enantiomers here, and you have also 2 specific modules for inorganic molecules and atmospheric components analysis. So the modules we used for the whole Rocknest campaigns is the GC5 modules that focus on medium-white organic compounds. In fact, each module is a mini gas chromatograph composed of an injection trap here, where the sample is flowed with helium, and at low temperature, the injection trap retains all the compounds. And these compounds are released quickly by flash heating up to 300 degrees C, the trap here, to the separative part, which is composed of chromatographic columns here. After this separative part, each compound can be detected with a TCD, which is a physical detector. And as it is a non-destructive detector, the exhaust of the module can be sent to the QMS for mass spectrometry analysis. So in this view graph, you can see a typical signal we can collect with SAM GCMS with a TCD signal in the upper part of this view graph and the QMS signal recorded simultaneously on the lower part. And we see here the analysis of a calibration mixture we used before the launch, which is composed of hydrocarbons here, which can be identified clearly because they are well separated with the gas chromatograph. We also identify some background compounds. So what happened in the Rocknest site? In fact, 5 samples were collected. You can see them here. And the 5th one was delivered to SAM for analysis. And in fact, from these samples, 4 different aliquots were analyzed with SAM with different operating conditions. These aliquots were sieved to deliver only fine grains to the system for the analysis. So what happens once the sample is delivered to SAM? In fact, it is put in an oven, which can be heated up to about 800 degrees C for about 20 minutes at rates of 35 degrees per minute. So during this time, the sample is continuously flowed with helium to be delivered to the directly mass spectrometer for EGA analysis. And we can collect part of this sample to be sent to the GC. The sample delivered to the GC is selected by selecting a range of temperature for which the sample is delivered there. And after, once the analysis is done, it can be delivered to the MS for GCMS analysis. So here is the result we obtained with the GC-TCD mode, meaning only the gas chromatograph. And you have the signal given for 3 of the 4 aliquots analyzed. And you can see here the ranges of temperature of the sample temperature selected for each of the aliquots. So in blue, you have a rather high temperature sample. In black, a rather low temperature sample. And in red, an intermediate one. And you can see on this main view graph that there is a big difference in this main peak observed here, sorry. And this peak is due to a big contribution of inorganic molecules, meaning mainly CO2 and also SO2 present in the sample and in the atmosphere. And the third inorganic molecule analyzed here is water. And we can see that from a sample to another, there's a big difference of content of water, which can be quantified with the TCD, and which is difficult to be quantified with GCMS analysis. Focusing on this part of the chromatograph, we see also minor contributions, but all these peaks detected here are not very numerous, but also they were also identified in the background measurements done prior to do analysis of Rocknest sample. So all the species identified here comes from a background signal in SAM. And we can focus on this peak here, which is due to a chemical reactant, which is on board the SAM sampling system to perform some wet chemistry to analyze the key compounds for astrobiology, such as amino acids or carboxylic acids. And we see that there are traces of these compounds in the system. So this analysis by GC-TCD is consistent with the EGA analysis, where we can track specific ions masses here, representative of different molecules. So you can see, for example, 32 for oxygen here. And we can retrieve all the inorganics I told about before, and also this chemical reactant present also in the signal here for M over Z equal 147 here. So the TCD gives consistent results compared with EGA. Moving, so this is a conclusion we can have from this detection. So Finally, we identify all the volatiles detected in the EGA mode with the GCTCD, and we can also conclude that there's a limited number of concentrated volatiles. So moving to the analysis with the MS, we also observe the inorganic molecules detected with EGA, and also background molecules. The only original molecules detected in this mode are presented here. These were tracked by plotting their specific mass as a function of time here, allowing to enhance the sensitivity of the measurements. So even if these compounds are not identified with GCTCD mode, they were identified with the GCMS mode. And these species are chloro, dichloro, and trichloromethane, as well as the chloropropene here. That can be also identified both by the retention time here, done by the separation with the column, and with a specific software developed for SAM, we can also reconstruct the mass spectrum of each molecule. So here you have an example of reconstructed mass spectrum for this species in red, which is compared with the standard mass spectrum in black given by the NIST library. And we see a perfect match between the two signatures, allowing a total confidence in the identification. So if we look at the EGA results, we can also identify the presence of chloromethane here and dichloromethane, which are the most abundant chlorine species identified in GCMS mode. And if we take care of the evolution of their signature here over temperature of the oven, we can see that the increase here is correlated with a decrease of the MTBS-TFA concentration in the sample, which drops at about 300 degrees C. If we compare this signature of MTBS-TFA in Rocknest analysis with the signature obtained in the background analysis, so this figure is not very fine, but we can see here in blue the signature of MTBS-TFA. We see that the signature drops at about 400 degrees C, so at a higher temperature than here. So we can suspect that in the oven of SAM there's a chemical reaction occurring which converts MTBS-TFA in chloromethane. And this conversion can be possible by the presence, for example, of perchlorates that can be suspected by the presence of these dioxygen peaks here. And you will have further information about this with the last talk done by Rafael Navarro-Gonzalez. But to test this assumption, we performed some laboratory experiments done by my colleagues in JSFC at Washington. And this laboratory experiment reproduced the GCMS here system and the sampling system with a pyroprobe, which is a pyrolyzer, allowing to heat the sample to the same temperature as on SAM. And when we perform these experiments, if we put pure calcium perchlorate in the system, we have a rather flat signature with the presence of benzene here coming from the injection trap. And when we put with calcium perchlorate MTBS-TFA, we see numerous peaks here, including the chlorohydrocarbons identified on SAM. So we are quite confident in the fact that the signature of chlorohydrocarbons identified in SAM mainly comes from the reaction of calcium perchlorate with MTBS-TFA. So to conclude on this part, the most important thing we discovered is the presence of chlorohydrocarbons, which can be inferred to the presence of perchlorate in the soil. And it shows that the sample treatment makes difficult the interpretation of a GCMS chromatogram, so we need to work a lot in laboratory to try to interpret them carefully. And we can say that there is no evidence of organics in the Rocknest samples from this analysis, but their presence cannot be ruled out due to our sensitivity and also the chemistry occurring in the oven. So in this slide, I summarize the main conclusions of this Rocknest campaign with the GCMS analysis. And I can add that for the future SAM analysis, as it was done at Yellowknife Bay, for example, we try to reduce the content of MTBS-TFA in the system by using a cleaning process. And we will try to identify organics in this environment. And I can add that you will have more detailed information about these measurements in a paper to be published very soon, I guess, especially one written by Laurie Leshin and one by Danny Glavin. And I wanted to end by acknowledging the French Space Agency that allowed us to develop the GC4SAM, and also all the people from NASA and the industry partners for making this mission and also these experiments possible. Thank you.
We have time for a very quick question. Is there one? Yeah, Jean-Louis.
I think
go to the mic, Jean-Louis, please.
It seems that you have a lot of SO2, so what is the origin of SO2?
SO2 is released by the pyrolysis of sulfates, in fact. So.
At least this is Martian.
Sorry?
This is SO2 genuine from Mars and not the stuff you show.
Yeah, no, it comes from Mars, yeah.
Thank you, Cyril. So we'll move to the last talk of the oral session, given by, I think we can say that, the only Mexican of the MSL science team, that I know, in fact. So Rafael Navarro-Gonzalez, and he will talk about the story of the perchlorate as seen by MSL and former mission. It's all yours, Rafael.
Thank you, Patrice and Javier. Well, this is the title of my presentation, a possible detection of perchlorates in the sample analysis at Mars. And this is the list of my co-authors. Well, the Mars exploration program, the objective is to seek to understand whether Mars was, is, or can be a habitable environment. In the last decades, the strategy that has been done is first to send missions to follow the water. We have done that successfully with Spirit, Opportunity, and Phoenix. The next phase has been to search for organics. The first mission to try to do that was Phoenix, but was unable to detect organics. And now Curiosity is looking for possible organics on the Martian surface. And if we are able to detect organics, the final quest will be to look for life itself. But actually, this has been done almost 40 years ago by the Viking mission. This is the most important mission that NASA has launched to Mars, and it has all the objectives to follow the water with the orbiters, to look for organics with an instrument similar to SAM, a GCMS, and finally to detect microbial activity through 3 experiments. These experiments are summarized here. In all cases, salt was taken from the Martian surface and introduced into different chambers. The first experiment was the pyrolytic release experiment, which tried to determine whether there were photosynthetic organisms on Mars. So the idea was to incubate salts with carbon dioxide or carbon monoxide in the presence of artificial sunlight. The results were very interesting. There was conversion of inorganic carbon to organic compounds, but it was not considered to be biological fixation because this fixation could take place during day or also during the night. The other experiment was the gas exchange experiment. The idea was to see if there were organisms, what kind of gases could exchange to the environment. The salt was moisture or was wet with some water and nutrients, and the results were very interesting. There was rapid release of oxygen, and that is interesting because photosynthetic organisms can release oxygen to the environment. However, in this experiment, the kinetics was very different. This was a sudden and abrupt release of oxygen. So these look more like a chemical reaction rather than biological reaction. And finally, it was the label release experiment, which consisted of incubating the salt with some nutrients and try to see whether these nutrients could be destroyed or metabolized by microbial organisms. This was the most controversial experiment of the Viking. And here are some of the results. In blue, you have the release of radioactivity. The compounds that were injected into the soil were with carbon-14. So as soon as the broth of nutrients was added to the soil, there was a rapid release of radioactivity with the kinetics exactly as that observed with terrestrial soils with microbes. To test whether this was indeed a biological activity, the soils were sterilized by heating them for 3 hours at 160 degrees, and then they were added this broth of nutrients, and you can see that there were no release of radioactivity. So this is exactly as it was done with terrestrial organisms. The researchers were very interesting because this indicated possibly biological activity. If the Viking soil was heated to not a high temperature, but just 50 degrees for 3 hours, the activity could still go on, but the strength of the activity was completely reduced. And if the soil was stored for almost half a year inside the Viking mission, and then that soil was incubated, the activity was very, very low. So these results indicated possibly the existence of biological activity. However, there was, as I told you before, a fourth experiment that has nothing to do with biological activity. It just intended to look for organics in the Martian soil. And since all living organisms on Earth are built of organics, it was logical to look for organics to see whether there was life. The results were very surprising. There was no detection of organic compounds on the Martian surface. Surprisingly, there was the detection of chloromethane on Viking Lander 1 and dichloromethane on Viking Lander 2. The concentrations levels were about 15 parts per billion to less than 1 to 40 parts per billion. And at that time, it was unlikely to assign these compounds to normal organics in the soil. They were done during the Viking mission experiments with desert soils from the Antarctica and the Mojave Desert. And in all cases, they were producing a different kind of organic compounds, but never they detected the presence of chlorohydrocarbons. So because these compounds were also not detected on the blanks, in any case, they considered that they were terrestrial contaminations, more likely coming from cleaning fluids. Even though chloromethane is a gas, it cannot be used as a cleaning fluid. And they speculated that chloromethane was produced either by the reaction of hydrochloric acid with possibly some acetone or some other compounds. In the last years, there was a very important discovery done by Phoenix. It was the detection of perchlorates in the Arctic sites. In this case, it was the first time that they analyzed for salts in the Martian surface, and there was the detection of perchlorate. This was a big surprise because actually the detector was meant to look for nitrates, but perchlorates are an interference for that detector, and in fact, they discovered that there was perchlorates in the Martian surface. In addition to the MECA identification, there was another independent identification used by TIGA, which heated the soil from room temperature up to nearly 1,000 degrees. And you can see a rapid release of oxygen. This oxygen was attributed to the presence of perchlorate, but one would expect also the release of chlorine species. No chlorine species were detected by TIGA, and the speculation or the explanation was that any chlorine species reacted with nickel in the oven, so nickel sequestered all chlorine compounds, and there was no possible chlorinated compounds observed. Nonetheless, this indicated the presence of perchlorates in the Martian surface. This was the first discovery of this compound on an Arctic site, And it was a surprise because we expected that the chlorine was actually in the form of chloride and not perchlorate. The discovery of perchlorate has important implications for future missions because the chlorine of perchlorate is completely oxidized to the highest level, +7. Because chlorine is surrounded by 4 oxygen atoms in a tetrahedral form, it is very stable. So thermodynamically speaking, it's a very strong oxidant, but kinetically speaking, due to its symmetry, is basically unreactive. And this has implications for the detection of past and future missions to Mars, because the missions so far hit the soils to look for the organics, and during the heating process, perchlorates can be destroyed, and they can burn the organics or combusted them. We did some experiments as soon as this was discovered with Atacama soils. We selected Atacama soils because we have done extensive studies before showing that the Atacama is a very good analog of the Martian surface, at least in terms of very low level of organics, and also the lack of microbial activity in the surface. And when we added perchlorate to the Atacama soils, we discovered that the small amounts of organic matter usually observed as benzene was combusted immediately. And surprisingly, we observed the formation of chloromethane and dichloromethane. So when I saw this, I came back to the discovery of these chlorohydrocarbons on the Viking results. And we reinterpreted the data, suggesting that Viking indeed detected perchlorates and possibly organics at mid latitudes. This has been disputed now by Beeman and Bala. They claim that these compounds were indeed solvents that were present on the spacecraft, or they were also on the Viking GC instrument. Surprisingly, there was no detection of these chlorohydrocarbons on their blanks. And also, there was no detection of hydrochloric acid. There's no way they can expect hydrochloric acid coming on the Viking from NASA. So this has been challenged by Beeman and Bada, and we have debated basically because they have done a very rigorous protocol for cleaning the spacecraft. These solvents are very volatile. It's very hard that they can be maintained on the instrument, or they can be released even when they open into the Martian surface. Fortunately, when we proposed this, we were almost ready to launch MSL. And so with MSL, we are now able to test this hypothesis. So we have done the first analysis on the Rocknest. We landed on August, but actually the first contact chemistry that we did was on the Rocknest sand after almost 2 months or 3 months of work on the Martian surface. CD has already talked about this. This is the dune that was selected for the study, and there were several scoops that were taken. The idea was to remove the possibility of organics on the scoop or the chimera, and actually the 5th scoop is the one that was analyzed. This is the GC, the SAM instrument that already Cyril talked about. And what is important is that we analyzed blank and 4 Rocknest samples. The size of the material was less than 150 microns. The sun was heated up to about 840 degrees very rapidly in 20 minutes at the rate of 35 minutes per second. And the oven pressure was about 30 millibars. These are the results in comparison with Phoenix. In black, you have the oxygen release observed at the Phoenix landing site. And in red, this is the oxygen release with Rocknest. You can see that there is a big difference, almost a 100 degrees difference between the temperature onset on oxygen. We have done experiments with the NASA GSC sun test bed that operates at about the same pressure, and also at UNAM in Mexico, but the ones in Mexico are done at atmospheric pressure. We have basically the same results, except that in Mexico there's a shift of about 100 degrees due to the operation of atmospheric system. But you can see that the oxygen that we observe at Rocknest is very wide. And if we compare with possible perchlorates that can explain that, the best match is for calcium perchlorate, which is in blue. There could be some magnesium perchlorate. This is the one that was observed at the Phoenix landing site. And there could be a small contribution due to some iron oxides or iron perchlorates. As Cyril mentioned, we also have evidence not only of the oxygen release, but there is evidence of chlorohydrocarbons. For instance, here you have chloromethane and dichloromethane, and these peaks are correlated with the decomposition of this region that we carry from Earth, is MTBSTFA. This is oxidized and combusted, and these chloromethanes are produced. In addition to the evolved gas analysis, these gases were trapped on the hydrocarbon trap and then analyzed by GCMS. And here you have the results of these chlorohydrocarbons. There is a big peak of chloromethane, and then dichloromethane, trichloromethane, and chloromethylene propane. So it's very interesting. We have confirmed the formation of these chlorohydrocarbons on Mars. The source of the chlorine is from Martian sources. The source of the organics is more likely coming from terrestrial sources. So one possibility is that we cannot still rule out is that some carbon could be indigenous to Mars, but the majority of the carbon is coming from either SAM or Chimera. But the source of chlorine is without doubt from Martian sources. And the proposed pathway for the formation of this chlorocarbon is the combustion and chlorination of these regions, producing chloromethane, dichloromethane, and trichloromethane, which has been observed in experiments using this compound. But also, it's only produced this chloromethylene propylene from the oxidation of this reagent. So in summary, these three chlorohydrocarbons and chloromethylene propylene are not present in the background levels. They are only produced when the SAM instrument is in contact with the Martian suns. So the source of this chlorohydrocarbon has to be partially Martian due to the chlorine coming from the sun. And the source of the carbon is either from SAM or from organics coming from the arm or something. There are various proposals for the formation of these perchlorates. The most logical is atmospheric oxidation. The chlorine can come from volcanic eruptions, or also chlorine coming from the dust. It can also occur in the surface by photooxidation, or also catalyzed by mineral, or even it can also be triggered by cosmic rays. And this mechanism suggests that the formation of perchlorate has to be global. So we have observed this perchlorate in the Arctic side. With SAM, we have detected in the equatorial region, and with Viking, we have evidence in mid-latitudes. In conclusions, we have the second identification of perchlorates in Rocknest. The first detection coming from from the Phoenix lander, and these results confirm our interpretation that the detection of chlorofluorocarbons in the Viking do indicate the presence of perchlorate, and this suggests that this is a global mechanism, and perchlorates should be present ubiquitous. And this has important implications for life, because microbes can utilize perchlorates to obtain energy. They also can act to lower the freezing temperature of water, but they also have implications for humans because perchlorates are toxic to men. Thank you.
Well, unfortunately, we don't have time for questions, but I invite you to meet Rafael at the poster session. The poster session is going to be on the red zone, and it's going to start around 5, from 5 to 7. So please, I will invite you, everybody, to go there. And thank you, everybody, for the 2 nice days that we had. We have received the congratulations from the divisions, from the Planetary Science Division. And it is thank you to all the speakers. Thank you very much, everybody.
Could you just